example, we're going to use an example where friction is doing work and causing the kinetic energy to decrease. So that in this case, we have a hockey puck, which is given an initial speed of 5.5 meters per second. It's sliding on ice that has a coefficient of kinetic friction of 0.05. The question is, how far does the puck slide before coming to rest? And we're going to solve this problem using conservation of energy. So again, we will gather our information. First thing we're going to do is draw a free body diagram for this puck. So we know that there's a weight due to gravity in the downward direction, and that's exactly balanced by the normal force of the contact force of the ice on the puck from below. We also know that there is a frictional force which is pushing in the opposite direction that the velocity of the puck is going. So if the velocity is moving the puck towards the right, then that frictional force is in the opposite direction. The energy of the system, in this case, we have to include the frictional force which will be doing work on the system, and that will be doing work against the kinetic energy to cause it to slow down. So in this case, we know that work, as before, is the force times the displacement, and the force in this case that's doing the work is the friction. It's the force that's causing it to slow down, and what we want to find is d, which is unknown in this problem. Starting from the same organization, we know that the final energy of this whole system is 0 because at the end there is no kinetic energy, and so all the work has been done. We also know that the kinetic energy at the initial is equal to 1/2 mv squared, where v is v naught, the initial speed. So using this equation idea, we know that work is equal to the negative of that kinetic energy. So we can replace the work with F times D again, as we had before. And using this equation, we can see that F is negative in this diagram that we've drawn here. So we have negative little f frictional force times D is equal to a negative 1/2 mv naught squared. We can replace little f with mu sub k times the normal force, and we can of course replace the normal force with the weight due to gravity because it's balanced in that direction. So the weight becomes mg, and that leaves us with this equation, which now has only one unknown, which is this distance d, our unknown that we're looking for. So we need to solve for that. First thing we can do is cross out the mass from both sides, and then we can also cross out the negative signs. We can divide the whole thing by mu sub k times g, and that gives us the distance, which is our unknown that we're looking for, on the left-hand side, and we get on the right-hand side v naught squared divided by 2 mu sub k times g. We can plug in our answers at the end here, so v naught is equal to 5.5 meters per second squared. The mu sub k is 0.05, and the g is 9.8 meters per second squared. When we do this, we can see that the distance that the puck will travel is 31 meters. We can check our units here at the end, and we see that d is, again, this v naught squared over g, basically, because 2 and mu sub k do not have units. So we get meters squared per second squared all divided by meters per second squared. The seconds squared on the bottom can go away. It gives us meters squared per meter, and that ends up with being meters. So we can see that the units work out for this problem.